pleasure to introduce our next speaker, who you've heard about already from Kate McGrath earlier this morning, Professor Martina Doblin, who is a Professor of Oceanography at UTS here and the current Director and CEO, sorry, I'm just multitasking here, CEO of the Sydney Institute for Marine Science. She's passionate about oceans, or has been from a young age, and she's been a marine researcher for over 20 years, leading highly successful research teams investigating the impact of climate change, harmful algal blooms, and more recently, the ecological impacts of emerging contaminants released into coastal waters. She's a board member of Australia's Integrated Marine Observing System and a member of the National Marine Science Committee, providing scientifically robust, practical advice on marine issues of national significance to Australia. Martina has a profile of scientific and public engagement and is an advocate for diversity in the science, technology and engineering professions, and has a strong interest in accelerating solutions for improving water quality in the urban ocean. So can't wait to hear from you, Martina. Thank you very much.
Well, it's great to be here. Thank you so much, Hognam, for asking me to present today. And I must confess to initially being, I guess, in the frame of a marine scientist, what have I got to offer to this audience? But the more I'm hearing this morning, the more I know that I need to be here, not only to share an ocean-based story, but to learn from you all and contribute to this integrated solution that we really have, I guess, a challenge to realise. So thank you again for having me. And here I'm going to provide a very environmental and high-level perspective on why a circular economy is needed. I want to also acknowledge the place that we're meeting here today and the lands from which you've come from to travel here to Sydney. It's also important for me to pay my respects to elders past and present, and to acknowledge that deep connection that Indigenous people have with their lands and waters, their saltwater country as much as their country and land country. Here these images, the picture on the left and the aerial photograph on the right, show this interconnectedness of the land with the ocean. And it's really that connectedness that is driving some of the narrative that I'll present in my story today. Importantly, I think traditional owners really understood and acted in a manner that really connected healthy country with healthy people. And it's this principle, I think, that I guess modern Australia, modern global way of living has absolutely, we have much to learn, as Lisa had indicated. We are at a point in the Earth's history where we need to urgently shift to a circular economy. We're taking too much, we're wasting too much, and we're emitting too much. We're using 60% more resources than the Earth has to offer that it can regenerate. We're throwing away billions of tonnes of waste, and we are exceeding our emissions targets where we're getting there with the renewables, but as Lisa said, we need to circularize the way that we produce and consume in order to meet emissions targets. Researchers have described this as a situation in which planetary boundaries are being exceeded. So 9 processes have been described that regulate the stability and the resilience of the Earth climate system, and 6 of them have been exceeded in the year 2023. So the safe operating space is the green space in the middle, and you can see in the large red wedges that we're seeing transgression of those processes in quite significant ways. And here I've highlighted climate change, biodiversity loss and nutrients that will become evident through the rest of my talk. This story of interconnectedness is one that I'll continue to reiterate, because if we focus on any one process in isolation, we realise there's an interconnectedness and that we cannot, I guess, just think that we're going to solve our problem by focusing on one process. When one boundary is transgressed, other boundaries are also at risk. Here it means that we're operating in an increasingly unpredictable environmental space and that we are increasing the probability of a major catastrophic shift in the environment. So we've reached a point where we cannot ignore this. So I wanted to use nutrients as my case study, and I have an ocean focus here, really to start to draw these examples together and how impacts are emanating beyond the land and into the ocean. So this is a satellite image showing a plume of dust that's swept out across the African continent. This has been transported into the ocean, and this is a natural process that has occurred for millennia and is fundamentally important to stimulating productivity in the ocean. Scientists are learning more and more about how iron is necessary for physiological systems in plankton to generate organic carbon, to capture nutrients, and to sequester carbon into the deep ocean. So we have this fundamental reliance on land-based materials reaching the ocean to stimulate ocean productivity. But climate change is really accelerating this transfer of materials. We've seen in the recent 2019-2020 black summer fires a huge amount of biomass that's been incinerated to generate pyrogenic aerosols, and that has led to massive extinction. In Australia, the estimates are some 3 billion animals perished in that single event alone. And climate change, as we know, we've got warming temperatures, we've got drying landscapes, increased probabilities of bushfires, and the consequence is very significant indeed for the way that our ecological systems are functioning. And those ecological systems are really fundamental to our health and the ecosystem services that those ecosystems deliver to us. Things like nutrient transformation, carbon sequestration. Not only this, bushfires combined with floods, which is what the region New South Wales experienced in the year following, is that these nutrients and other materials generated from the bushfires are being mobilised again out into waterways and into the ocean through this delivery vector of water. So here I wanted to show you some data. I'm a scientist after all. Research that we're doing here at UTS has actually used the air conditioning filters from our buildings to basically capture this aerosol particulate matter. These filters, of course, protect us and improve the air quality inside our building system, but they make excellent sampling devices for aerosols. And here I'm showing some data from filters that captured both bushfire aerosols and also urban emissions. And basically the headlines are that the wildfire aerosols contain far less phosphorus than urban emissions. They contain less nitrogen than urban emissions. Here I want to mention though that the solubility of nitrogen in bushfire emissions is much higher. And importantly, the wildfire emissions contain much more iron than urban emissions. So these are fundamentally important nutrients for biological systems, both on land and in the ocean. And indeed, when we look at the effects of those fires, the aerosols were swept out across the ocean, right across the basin of the South Pacific. You can see here the aerosol distribution from November 2019 through to February 2020. And you can see their extensive distribution eastward. And this is, I guess, mirrored by the picture of deposition of that material. And this stimulated the, I guess, very extensive phytoplankton blooms that occurred in the ocean that spread across thousands of kilometres. Look like this in aerial view, but this is a plot showing the amount of phytoplankton conditions across the year, and the bars in red show you just how much of the production was stimulated from these aerosol emissions that were deposited into the ocean. So we're losing materials from land that get transported into the ocean, and this is very important that they go beyond our exclusive economic zone, and we actually donate those materials to other countries. So the mobility of nutrients is an important thing about its materiality that is an important consideration in the circular economy. And I guess the figures show that there was just as much carbon dioxide released in those bushfires as was taken up by the plankton in the ocean. That there was a huge amount of nitrogen that went along with that. Some 28 million tonnes of nitrogen were basically exported from land into the ocean over that 6-month period. Massive, really, when you think about the scale of that single event. And of course, farmers have a very real understanding of what that means for their businesses. In a more sort of business as usual setting, there are of course regulated discharges of nutrients into Australian coastal waters through wastewater treatment plants. And here I just wanted to give you a sense of the benchmark here. I've used, so let me just indicate that there are some 192 coastal outfalls for where this material is released. And here in the vicinity of Sydney, we have one of the largest wastewater treatment outfalls nationally. If I look up the loads, this is available in the public database, and if I do the calculation, we're releasing some 4,000 tonnes of nitrogen every 6 months from that wastewater plant. Far, far less than what was released in the single event of the bushfire, just to show you there the order of magnitudes difference here. So importantly, though, that these are regulated discharges. They were intended, the wastewater treatment plants are obviously intending to reduce the possibility of excess nutrients in our coastal systems. Not all countries have this degree of regulation. This is an image of a very large algal bloom in a coastal city in Indonesia. My Indonesian student is looking at harmful algal blooms in this region, and of course the unintended, the consequences of these large blooms are massive fish kills, potential human hospitalisations and fatalities if those blooms contain toxins. So there are huge implications for releasing nutrients and the harm that they can create, which is why wastewater treatment plants are so important in managing nutrients. We do, however, have releases of nutrients and other materials into our coastal waterways through simply rainfall events. This is an image that shows the number of sewer overflow points in Sydney Harbour. And we know that rainfall and stormwater inputs, in fact, release more contamination into the harbour than through regulated waste discharges. And so there are things that we're not controlling in our current systems that are potentially causing impacts to the environment. And here the concern, of course, is human contact with water. If people are swimming, that they may in fact be in contact with pathogens and other harmful contaminants. We know that this is an important process globally. Recent research has shown that the amount of pharmaceuticals in our rivers and freshwater systems is increasing. This analysis sampled over 100 countries across all continents, over 1,000 sampling sites along 258 rivers. What one would call a representative sampling across the globe. And here are the results that show the pharmaceutical concentrations in nanograms per litre here on the y-axis and the respective river source on the x. Here just a few highlights around these upper 100 or the 10% most contaminated rivers come from 15 countries listed here. There's some interesting observations to be made around emerging economies there. But Australia also features in this census that there are pharmaceuticals that are entering our waterways that are potentially compromising ecological systems. They, of course, are designed to keep humans healthy, the use of antibiotics, for example, but antibiotics, by definition, kill bacteria, and bacteria are fundamentally important parts of natural systems. So, we've been working with the Australian federal government to really understand contamination of coastal waters, really to help them gain an evidence base around how effective current wastewater treatments are with respect to emerging contaminants. And here I've got a very early view of some of our work. We've done a specially structured sampling design. This is an example of one of our locations at Villanelle. There's a coastal outfall here just off the beach. When we look at the contaminants across those spatially structured transects, we see not only inputs of nitrogen that are greatest here at the source that dissipate with increasing distance from the outfalls. We're seeing things like metals and microplastics coming from those sources. So here we have to make the point that we're not just seeing nutrients as part of this environmental challenge, but contaminants of various forms. So circularising our systems and extracting value from nutrients might involve thinking about other components of those wastewaters. So I guess here I wanted to pause for a moment and to say that there are some implications about the way that nutrients are flowing from land into the ocean. They're increasingly being mobilised in our climate-affected world.